Our main subject for this sky at night is going to be the Great Nebula in Orion. But first of all, there are two people whom I very much want you to meet. Two of Britain's amateur astronomers, both of whom have made really interesting discoveries quite recently. Roy Panther has discovered a comet. David Branchett has discovered, well, we thought it was a nova or new star, but now I think that's a bit doubtful. What is it, David?
Well, we don't really know yet, Patrick, but all the indications are that it is indeed probably a newly discovered eruptive star.
Where exactly is it?
Well, it's located in the constellation of Scutum, just southwest of star Beta Scuti.
And it's very low down at the present moment.
Well, I discovered it with my handheld 15 by 8 binoculars on the morning of January the 18th, and it was only 6 degrees above the horizon when I discovered it.
Well, that's pretty remarkable, but you have now got a finder chart which shows exactly where it is, and it's very close to the famous star cluster M11, Messier 11, the so-called wild duck. And there's a famous variable star R Scuti, there's Beta Scuti on the other top, and there is your object. Well, I don't think it can be an ordinary nova.
No, indeed, it's very fast. The latest magnitude estimate puts it below 11.7 already, which is extremely fast.
Has anybody else seen it visually yet?
Well, there was a report from a chap called Jim Morgan in Arizona, but he did express some dates afterwards, but it's possible he saw it at about magnitude 10.
Well, I've certainly failed to do so. It's just too low down. And, of course, there's going to be some weeks now before it comes back into a darkened sky.
Indeed, I think it will be probably another month before the professionals can really get their teeth sunk into it.
And only then shall we really know what it is. Anyhow, many congratulations, David.
Thank you, Patrick.
Roy, now, you have discovered a comet, but you were using a telescope, not binoculars.
I was using a telescope, yes. An 8-inch reflecting telescope.
One you made yourself?
Yes, 10 years ago.
Let's have a look at the comet itself. I think this is not your photograph, is it?
No, it's taken by Brian Manning.
And it does show the comet very nicely indeed. The other stars drawn out into short trails. Were you making a systematic search?
Yes, I was. Yes.
Well, of course, unlike David's nova, if nova it is, this at least is in the far north of the sky. I know it was in the constellation of Draco when you discovered it, and that's not very far from the pole star. And there's the comet at the present moment, and it's going to track up, and I gather it will pass actually between the pole star and the celestial pole around about March the 11th.
That's right, yes.
At the moment, is it brightening or getting fainter?
It's a little bit brighter than when I first discovered it, and I think the brightness will hold for several weeks.
So at least we're going to have a comet in the same field as the pole star. Now, it's been a long time since that happened.
Yes.
Well, again, many congratulations to you also. And do remember that discoveries of this kind are not sheer luck. You can occasionally make chance discoveries. It's been done. But in this case, both David and Roy were carrying out systematic searches, and they know the sky very well indeed, so that if any unexpected object turns up, they will recognize it, as in fact they did. And I think it was a really magnificent piece of work. Well, now, on to our main topic for tonight. I think there's no doubt, you know, that Orion is just about the loveliest constellation in the entire sky, and it dominates the scene all through winter evenings. And this photograph was taken with an unguided camera, one I took myself down at Chelsea, and you can see there that the stars are drawn out into short trails. But Orion has two particularly brilliant stars. They are Betelgeuse and Rigel. Well, Rigel's a real celestial searchlight, something like 60,000 times more luminous than our sun. Betelgeuse isn't as bright as that, but to make up for that, it's extremely large. It's a huge red supergiant. And you know, you could take the whole path of the Earth around the sun and put it inside the globe of Betelgeuse. And if you have been looking at Orion, well, Betelgeuse is a variable star, and this year it's been absolutely at its best, and it's very little, if at all, inferior to Rigel. At other times it's very considerably fainter. But I want to talk now about the Hunter's Sword. And in the Hunter's Sword, you will see a misty patch. You can see it quite easily with the naked eye, and when it's photographed with large telescopes, well, it really is glorious. That is the Great Nebula in Orion, otherwise known as Messier 42, M42, because it was the 42nd object in Messier's famous catalogue of clusters and nebulae, which was drawn up now 200 years ago. As I've said, it's quite easily visible with the naked eye as a smudge, and binoculars show it well, and small telescopes give an excellent view of it. This is a photograph taken by Commander Hatfield at Sevenoaks with his 12-inch reflector, and through a telescope it does look very much like that. Only you do need photographs taken with major telescopes to bring out the real details, and this was taken with the Palomar 200-inch. But there's one thing I do want you to bear in mind. Those colors are genuine, all right, but you won't actually see them if you look at the nebula through the eye end of a telescope, because the colors are just too faint, but they really are there. Now, there's more nebulosity in Orion, as well as the visible sword handle. There is, for example, the Horse's Head Nebula, which is close to the bottom star of Orion's belt. And seen like that, it really does look very much like the head of a knight in chess. But there's no basic difference between a bright nebula and a dark one. It all depends whether or not there are suitable stars near at hand to light the gas and dust up, and sometimes make it shine a bit on its own account. In the case of the Orion Sword Nebula, there is such a star, or rather a group of stars. It's the famous multiple Theta Orionis, otherwise known as the trapezium. And you can see the trapezium there quite easily, not far from the center of your screen, and you will see all those 4 stars very clearly with any small telescope. And they are actually lighting up the nebula and making it shine on its own account. But, as I say, a bright nebula and a dark one are essentially the same thing. Let me show you what I mean. Here we have an artificial nebula. It is, in fact, a mass of cotton wool, and that's what it really looks like. Now, just imagine it's being lit by stars from one side only. Suppose they're lighting it from the right-hand side of your screen, where we are seeing then a bright nebula. But if you look from the other hand, the left-hand side, where there's nothing to light the nebula up, then you will find that the nebula is dark. And you can only detect it then because it blocks out the light of stars beyond. But it is the same nebula, made up of very thin gas and dust. The Orion Nebula is rather more than 1,000 light years away, and it's of special importance to us because this is a place where new stars are being created out of the interstellar material. It is, in fact, a stellar birthplace. But recently, we've been learning more unexpected things about the Orion Nebula. There are some very curious objects deep inside it. So deep that we can't actually see them visually, but we've tracked them down and we know that they are there. And their nature is still very much of a mystery. Well, one man who's been doing a great deal of research on this is Dr. John Beckman of Queen Mary College. We're delighted to welcome you back to the sky at night, John. And you have, in fact, been doing a lot of work on the Orion Nebula.
Yes, it's an object which is very familiar to me and to various other astronomers. Yeah. I think the best way to illustrate it is to look at this, which is the best optical picture ever taken of the Orion Nebula.
Superb.
It was taken over 15 years ago at the Lick Observatory at the University of California, while I was there, in fact. It was taken with the 36-inch Crossley reflector, a reflector that was made over 100 years ago in England and has superb optics. What's special about this photograph is that it was made by a 3-color separation process, which gives a very true representation of the color. This particular picture is unique that there's only one copy of it in this country. It's a little bit the worse for wear, but there's no way one can get another reproduction of it. You can see the green part of the nebula glowing in the light of ionized oxygen. And you can also see very vividly a red part, which is the place where unionized hydrogen is glowing.
And of course it does show the trapezium very well indeed. There's 4 bright stars making up Theta Orionis. Very hot and bluish white. But there are plenty of other hot stars in the Orion Nebula. And they also send out a great deal of ultraviolet.
And the ultraviolet radiation has one effect. The nebula glows and is above all dynamic. When we examine the light with a spectrograph, which can reveal the velocities inherent in the gas, we can show that the gas is expanding very rapidly outwards and impinging on the surrounding nebula, on the surrounding gas.
Well, it's visually lovely. But let's now come to the infrared. We've got to remember that visible light makes up only a very small part of the total range of wavelengths or electromagnetic spectrum. Over to the shortwave end, we have ultraviolet, and then X-rays, and then the ultra-short gamma rays. On the long wave end, we have, first of all, microwaves, then we have infrared, and then we come to the long wavelength radio waves. And the infrared studies have told us a great deal about the Orion Nebula. Over in California, at the California Institute of Technology, known as Caltech for short, studies were made at Mount Wilson by Beckman and Neugebauer. And in infrared, they discovered a very curious source deep inside the Orion Nebula, so that we can't actually see it. There's nothing visually there at all. But in infrared, I think I'm right in saying it's the brightest object in the whole sky. For it's a BN or Beckman-Neugebauer object.
It is the brightest object in the whole sky, and it peaks, it shines at a wavelength 3 times that of visible light, in what's called the near-infrared, 1.5 microns wavelength. A few years after this discovery, a probably even more interesting discovery was made by the astronomers Kleinman and Lowe, who had developed techniques to look in the far infrared at 100 microns wavelength, that is to say, over 200 times the wavelength of visible light. And they found an object which was called the Kleinman-Lowe object, or KL as it's now known. This is, again, the brightest source in the whole sky. It's within the Orion Nebula, and it's a far infrared source.
So we have BN and KL, and I believe known affectionately as Binkle.
Yes, that's so.
Is there any chance at all that they really are either the same object or different parts of the same object?
They are not the same object. They are distinct. They are as distinct as any pair of stars would be. They are both components of the nebula, but they are distinct sources.
Well, let's try and pinpoint their positions then. We can do that on this magnificent photograph, because you know exactly where they are. There is the trapezium, Theta Orionis, and here are BN and KL. And just exactly what they are, we'll come to in a few moments. But meanwhile, let's look beyond the visible nebula, because after all, there's much more to it than that. And I remember you saying once that the visible nebula is merely the tip of what you called an interstellar iceberg.
You can see that by looking at a map that was made a couple of years ago by the members of the Queen Mary College Molecular Astronomy Group. It's a map made in the emission from carbon monoxide molecules. As techniques have advanced, radio astronomy methods have overlapped into the infrared. It's now almost a matter of opinion whether you call it radio astronomy or infrared astronomy. And by this technique, it's possible to make a map like this at 1,300 microns, that is 2,500 times the wavelength of visible light. And you can see how big the cloud is by imposing on the visible photograph that we saw before just the middle few contours of the other map. There it is, just the middle few contours. You can see that the visible Orion Nebula is very small compared with the carbon monoxide cloud. The cloud itself is also much cooler. The cloud itself varies between 100 degrees and 10 degrees above absolute zero.
Well, that's still minus 260 centigrade, so your analogy of an interstellar iceberg wasn't very far out. But when you're talking about carbon monoxide, I think I'm right in saying that it's not really the carbon monoxide which interests us. What we want to find out is the distribution of the hydrogen, because it's the hydrogen which is all important. And the trouble is that hydrogen is very shy about showing itself. But luckily, hydrogen affects the molecules of carbon monoxide and makes them radiate. And therefore, by studying the carbon monoxide, we know where the hydrogen is.
Yes, we can see the carbon monoxide and therefore the hydrogen clouds spreading out, centered on the position of KL, but the clouds fill a very large portion of the sky. In other words, the Orion Nebula and KL itself and the whole of the first map are quite tiny compared with these enormous clouds of molecular hydrogen which fill several degrees of sky.
Yes, I suppose if our eyes were differently constituted, we'd find most of Orion filled with nebulosity, because it really is a very extensive cloud, and that visible nebula is only a tiny part of it. But let's come back now to these mysterious infrared sources. We've talked about BN. Let's put in KL, after we do know exactly where it is. There's KL.
Yes, KL is interesting because not only can we see it very, very strongly in carbon monoxide, it is the strongest far infrared source in the sky, it's also the strongest carbon monoxide source in the whole sky. But we can also see, by looking at the carbon monoxide, that it contains streams of gas moving at very, very high velocity indeed. Now, the way we examine it is by taking our carbon monoxide spectrometer, and we can look at the KL point itself, and we can look at a point nearby. And at both of those points, we see a very bright, sharp spectral line. But whereas nearby, the line is very narrow, on KL itself, the line has a broad, triangular set of what are called wings. And those wings represent gas moving at very high velocities, 100 kilometers per second, which is about 170,000 miles an hour.
In other words, it's incredibly energetic. But let's come now to the main point, John. What exactly is KL?
Well, it's probably a protostar. When stars form, they form out of globules of interstellar dust and gas. Those globules shrink under their own gravitational field until the temperature at the center is hot enough to ignite the nuclear fuel, and then you have a star. But before that happens, the stars are heating up, and they're rather large, and in fact they aren't stars, they're called protostars, and that's what a protostar is. Now, during that phase, the surface area of the object is very big, and it's giving out a lot of radiation. And this radiation can accelerate the surrounding dust and gas. The acceleration continues until the dust and gas are moving at very high velocities indeed, supersonic velocities, whereupon they form a shock front. And in this shock front, at the edge of the object, lots of interesting molecular emissions occur.
Well, that's all very well. I think it's the theory you favour yourself, isn't it? But wouldn't a rapidly spinning star give very much the same effect?
It would give a similar effect kinematically. That is, if you examine the carbon monoxide spectrum, you would see effects such as are seen from a spinning object as well as from an expanding object. And one particular piece of evidence which rather impresses some people, including, for example, Peter Phillips of our own group, is that if you look off to one side of KL, these wings that I was mentioning before are asymmetric. One of the wings is emphasized. If you look off to the other side, the other wing is emphasized. And that's exactly the kind of phenomenon you would expect to see from a rapidly spinning object. So that is a rather possible clue.
Well, we talked about radio astronomy earlier on. It almost overlaps infrared now. Has radio astronomy itself told you anything particular?
A beautiful experiment done by radio astronomers fairly recently examined the water vapor mazes which surround KL. KL is surrounded by a set of mazes which appear, from the radio measurements, to be expanding outwards symmetrically at the same sort of speed, about 170,000 miles an hour, as we see in the carbon monoxide flows. And that, in fact, would favour the protostellar expanding model.
Well, I believe there have been some very recent results, and made even since we planned this program.
That's so. I've just returned from an observing trip to the British Infrared Telescope at Mauna Kea in Hawaii. And while I was there, I had the opportunity to discuss with Sarah Beck, a young American astronomer, some of her most interesting recent results in the near infrared, where she has an instrument which gives higher angular resolution than we can get. That higher angular resolution means that she can look at objects on a smaller scale, and she seems to see not one protostellar center of activity, but a little cluster, lots of different points expanding at high velocity. And this will be even more exciting than a single protostar.
You might even see them evolving.
You might indeed see them evolving with time, yes, although this would be a very difficult set of observations.
So it looks, in fact, as though BN is an ordinary, very massive, very luminous star, and KL is probably either a star that's just forming or a whole group of stars just forming.
And if it were a protostar, it would be an extremely useful and nearby opportunity to observe this kind of stellar birthplace.
Well, certainly we're going to have exciting results in the near future. John, thank you very much, and all good wishes for your research. So the Orion Nebula is interesting. Do go out and look at it. You'll see it there in the Hunter's Sword, over 1,000 light years away. And when you look at it, you're looking at one of those places which we know to be an area where new stars are being born. Good night.